In 1983, physicists stopped measuring the speed of light. They declared it 299,792,458 meters per second, fixed into the foundation of every ruler and scale on Earth. And that number is the geometry of time itself, the boundary where cause and effect hold together. We will meet the astronomer who first measured this in 1676. Einstein's two postulates come next, and they shatter everything we thought we knew about time. Then comes Feynman's discovery that light explores every path in existence before the straight line wins. Subscribe if this is your kind of question. We begin. In the winter of 1676, a Danish astronomer named Ole Romer was doing something that bordered on punishment. Every clear night from the Paris Observatory, he trained his instruments on Jupiter and watched its innermost moon, Io, vanish behind the planet's shadow and reappear on the other side. The event happened with clockwork regularity, once every 42.5 hours, and astronomers had come to rely on it the way navigators rely on a lighthouse. Io was a celestial timepiece, arguably the most precise available to science, and Romer had been assigned the task of logging its schedule with enough precision to allow ships at sea to determine their longitude. The job required patience more than brilliance, and for months, nothing unusual appeared in his notebooks. Then the clock started drifting. Romer noticed that across the autumn months, as Earth moved through its orbit to the far side of its path around the solar center, Io's eclipses were arriving progressively later than his tables predicted. A few seconds, then a minute, then accumulating into a lag of several minutes over the course of the season. When Earth swung back around toward Jupiter the following spring, the eclipses began arriving early, slowly recovering the lost time. The pattern was unmistakable and perfectly correlated with Earth's position in its orbit. Every other astronomer at the Paris Observatory had seen the same discrepancy and attributed it to imprecision in the original measurements or to some perturbation in Io's orbit. Romer reached a different conclusion, one so unusual that even he took months to fully commit to it. The delay, he reasoned, had nothing to do with Io. It had to do with distance. When Earth was moving away from Jupiter, the light carrying each successive eclipse had farther to travel than the light carrying the one before it. The cumulative lag was the universe itself communicating a travel time. Light was not arriving instantly. Light was taking time, measurable time, enough time to matter at the scale of planetary distances. In a world where the speed of light had been assumed, without serious debate, to be infinite, Romer was proposing that the universe had been holding a secret behind every sunrise and every shadow ever cast on Earth. He presented his analysis to the Paris Academy of Sciences in September of 1676 with a specific prediction. The eclipse of Io expected on November 9th would arrive 10 minutes later than the tables said. The eclipse arrived on schedule, as Romer had forecast, and the prediction held. The head of the Paris Observatory, Giovanni Cassini, was unconvinced. He had seen similar patterns before and doubted the interpretation. Most astronomers followed Cassini's lead. The idea that light traveled at a finite speed had been debated since antiquity, argued over by Galileo, and never settled. And one reading of Io's timing record was not about to close the question for a community inclined towards skepticism. What Romer had done, however, was irreversible. He had shown that the discrepancy scaled with distance, that it reversed when distance decreased, and that it could be used to make a verifiable prediction about a future astronomical event. That was the structure of a measurement, even if the precision was low and the skeptics were loud. The speed of light had gone from a philosophical question to an empirical one, and the number would now have to be extracted from the universe rather than assumed away. The extraction would take 2 more centuries, and the work of obsessive, brilliant people who could not leave it alone. The first of them would not need Jupiter at all. Romer's argument rested on a specific calculation, and he made it with the tools available to him. which meant using a rough estimate of the distance between Earth and Jupiter at different points in the year. He reasoned that the total accumulated lag he had observed, somewhere around 22 minutes by his reckoning, represented the time light needed to cross the full diameter of Earth's orbit, the widest possible separation between Earth at one end of its path and Earth at the other. Divide that diameter by that time, and you had a speed. The figure he worked with for the diameter of Earth's orbit was drawn from the best contemporary estimates, and those estimates were too small by a significant margin. The actual diameter is roughly 186 million miles. Romer's inferred transit time was also too large. Modern measurements put the true crossing time at about 16 minutes and 40 seconds, not 22. These two errors compounded in a way that pushed his final speed estimate well below the correct value, arriving at somewhere around 137,000 miles per second, when the true figure is closer to 186,000. He was off by more than a quarter. What matters is that he had the correct structure. The delay grew when Earth receded, shrank when Earth approached, scaled linearly with the change in distance, and he had already used that relationship to forecast the November eclipse correctly. The logic was sound even where the numbers were imprecise, and in science that hierarchy matters enormously. A wrong number derived from correct reasoning can be improved. A correct number derived from faulty reasoning collapses the moment the data improves. The Dutch physicist Christiaan Huygens was one of the few contemporaries who accepted Romer's conclusion. He took the timing data and the best available estimate of the astronomical unit, the Earth to stellar center distance, and worked through the calculation independently, arriving at a value of roughly 1,000 Earth diameters per second. That translated to somewhere around 137,000 miles per second, consistent with Romer's result. In 1728, the English astronomer James Bradley found independent confirmation from an entirely different phenomenon. Bradley was attempting to detect parallax, the tiny apparent shift in a star's position as Earth orbits across its diameter, and instead found something stranger. Stars were displaced from their expected positions in a pattern that matched Earth's orbital velocity rather than its orbital position. The effect, which Bradley named stellar aberration, was the result of light having a finite speed combined with the motion of the observer. If you walk through falling rain, the drops appear to come at an angle. Bradley was walking through a rain of starlight, and the stars appeared to lean slightly in the direction of Earth's motion. He calculated a speed of approximately 185,000 miles per second, within less than 1% of the modern value. Romer's interpretation had been right. The universe had taken 52 years to confirm it properly. By 1849, the measurement of light speed had graduated from an astronomical inference to a laboratory ambition. What it required was a way to time something crossing a distance small enough to fit on Earth, using instruments precise enough to capture the elapsed duration of a fraction of a heartbeat. The French physicist Hippolyte Fizeau built exactly that device on the hills north of Paris, and the principle behind it was so elegant that it reads less like an experiment than like a piece of mechanical poetry. Fizeau directed a beam of light from a lamp at Montmartre toward a mirror mounted on the heights of Montmartre's neighboring hills, approximately 8.5 miles away. Between the lamp and the mirror, he placed a spinning cogwheel with 720 teeth and 720 gaps cut evenly around its rim. The beam would pass through one of the gaps on its outward journey, travel the 17-mile round trip to the mirror and back, and then arrive at the wheel again. At slow rotation speeds, the gap that had let the light through was still there when the beam returned, and the light made it back to the observer. Increase the rotation speed, and eventually, the wheel moved fast enough to bring the next tooth into the beam's path on the return trip, blocking the light entirely. Increase the speed further, and the wheel moved again, this time bringing the next gap into alignment, and the light came through again. The critical rotation rate, the speed at which the returning beam threaded cleanly through the next gap, gave Fizeau everything he needed. He knew the distance the light had traveled. He knew the geometry of the wheel and which gap had aligned. He could calculate exactly how much time had passed between the beam leaving and the beam returning, because the wheel's rotation rate told him precisely how long it took to advance by one gap. His result was approximately 195,000 miles per second, about 5% above the modern value. That error came from the difficulty of pinpointing the exact rotation rate at which the light faded and returned, a determination that required human judgment over the threshold of the lamp's brightness. Later experimenters with better instruments and finer cogwheels would improve on him substantially. The French physicist Léon Foucault replaced the cogwheel with a rotating mirror in 1862, trimming the error to well under 1%. But what Fizeau had established was the principle. Light speed could be extracted from terrestrial equipment in a Paris suburb without consulting Jupiter. The sky was no longer the only laboratory, and the era of obsessive precision was underway. No one pursued that precision with greater devotion than Albert Michelson, and few scientific careers have been as thoroughly organized around a single physical constant. Michelson measured the speed of light at the United States Naval Academy in 1879 at the age of 27 and arrived at a value of approximately 186,000 miles per second with an uncertainty of less than 30 miles per second. Remarkable for the era, the result was good enough to establish his reputation. It was not good enough for him. Over the following decades, Michelson redesigned the problem repeatedly, constructing instruments of increasing mechanical refinement and running them on progressively longer baselines where small fractional errors translated into smaller absolute ones. His 1926 measurement was the culmination of that long campaign. He used a rotating octagonal mirror mounted on Mount Wilson in California, aimed across 35 miles of open mountain air at a fixed mirror on the peak of Mount San Antonio. Light sent from the rotating mirror would return from Mount San Antonio and strike the octagonal mirror again. If the mirror had rotated to the correct angle during the round-trip travel time, the returning beam would be redirected into the measuring telescope. From the rotation, speed, and geometry, the travel time could be extracted with extraordinary accuracy. His result was 299,796 kilometers per second, within 4 kilometers per second of the value that would eventually be fixed as exact. Michelson had already received the Nobel Prize in Physics in 1907, the first American to do so, for his optical precision instruments and the investigations he had conducted with them. The 1926 measurement was widely understood as the definitive word on the subject. But the paradox sitting at the center of his career was this. Michelson's most famous experiment had produced not a measurement of light speed, but a measurement of something that was not there. The instrument he and Edward Morley had built 39 years earlier had been designed to detect the medium light was presumed to travel through, and it had found nothing whatsoever. The speed of light, refined to such extraordinary precision, had no anchor in the universe. It was a number floating in empty space, pointing to a crisis in physics that Michelson himself never fully resolved. By 1972, the technology for measuring light speed had outrun the precision of the meter itself. A team led by Kenneth Evenson at the National Bureau of Standards in Boulder, Colorado, used stabilized lasers to measure the frequency and wavelength of light simultaneously and directly, allowing the speed to be calculated from their product without the geometric approximations that had limited all earlier methods. Their result was 299,792,458 meters per second, with an uncertainty of just over 1 meter per second. The measurement was so precise that the uncertainty in the meter, which was still defined at that time by the length of a specific platinum iridium bar stored in Sèvres, France, contributed more error than the experiment itself. This asymmetry contained a straightforward implication. The meter was now the limiting factor, and the meter was improvable. 11 years later, At the 17th General Conference on Weights and Measures in 1983, the international body that governs physical measurement did something that has no real parallel in the history of science. They stopped measuring the speed of light and started using it to define distance instead. The meter was redefined as the length of the path traveled by light in a vacuum during exactly 1/299 millionth of a second. The speed of light was assigned the exact value of 299,792,458 meters per second, with no uncertainty, because the uncertainty had been absorbed into the definition. The platinum iridium bar in Sèvres, which had served as the world's standard of length since 1889, was retired. Every ruler, every tape measure, every surveying instrument, every atom interferometer, every laser ranging system on Earth became, in a precise formal sense, a device for counting how far light travels. The speed of light was no longer a fact to be extracted from the universe. It was a declaration woven into the foundation of measurement itself. Any future experiment that produced a different number would be understood not as a refinement of c, but as a redefinition of the meter. The question of how fast light travels had been answered so definitively that answering it again was, formally, impossible. Before anyone understood what light was, before Maxwell wrote his equations, before the interferometer existed, virtually every physicist in Europe carried a belief about the fabric of the universe that seemed as necessary as the belief in air. They called it the luminiferous ether, a term borrowed from ancient Greek philosophy and filled with 19th century mathematical content. It was the medium through which light waves propagated, invisible and all-pervading, filling every apparent void in the cosmos, the way water fills the depths of the ocean. The analogy was more than metaphorical. Sound required air. Water waves required water. Every wave in the physical world required a medium, and light was a wave. Therefore, light required a medium. The logic was not merely plausible, it was airtight. The ether carried specific properties that the physics demanded. It had to be extraordinarily rigid, because light travels faster than any mechanical wave ever measured, and wave speed scales with the stiffness of the medium. It had to be perfectly transparent, because light from distant stars reached Earth without apparent absorption. It had to permeate all matter without measurably impeding planetary motion, since Earth had been orbiting the stellar center for billions of years without slowing down. It had to be absolutely stationary, an immovable frame through which everything else moved, because without a stationary reference frame, the speed of light would be relative to the observer rather than absolute. Lord Kelvin, who had organized much of thermodynamics and given physics its temperature scale, regarded the ether as real as the floor beneath his feet. Hermann von Helmholtz, who had formulated the conservation of energy, built his theory of electromagnetic oscillations on ether foundations. James Clerk Maxwell, whose equations predicted the speed of electromagnetic waves with uncanny precision, spent years attempting to construct a mechanical model of the ether that would explain how electromagnetic disturbances propagated through it. The entire theoretical architecture of 19th century physics, as sophisticated and successful as it was, had been built on this assumption, and the assumption was about to be tested. The experiment that Michelson and Edward Morley built in 1887 was not designed to find the ether. It was designed to measure the speed at which Earth moved through it. The distinction matters. By 1887, the existence of the ether was not in question. The open problem was its precise properties, and the most tractable version of that problem was determining how fast Earth traveled through the stationary medium as it orbited the stellar center at roughly 18.5 miles per second. Measuring that velocity required detecting the slight difference in light speed between beams traveling with the ether wind and beams traveling across it, the same way a swimmer moving with a current covers the same distance faster than a swimmer moving against it. Michelson had invented the interferometer a decade earlier, specifically to make this kind of measurement, The device split a single beam of light into two perpendicular paths, bounced both paths off mirrors, and recombined them. Any difference in travel time between the two paths would show up as a shift in the interference fringes, the alternating light and dark bands produced when the two beams combined. The apparatus Michelson and Morley constructed for the Cleveland experiment was mounted on a massive sandstone slab, floated on a pool of liquid mercury to allow smooth rotation without vibration. They calculated that Earth's orbital velocity through the ether should produce a fringe shift of about 4/10 of a fringe, well within the instrument's ability to detect. The experiment ran over 4 days in July. They rotated the apparatus through every orientation. They took measurements at different times of day, at different positions in Earth's orbit. They found a fringe shift consistent with 0, less than 1/100th of the predicted value. The ether wind, if it existed, was undetectable. George Fitzgerald proposed within 2 years that material objects contracted in their direction of motion through the ether by precisely the right factor to cancel the expected signal. Hendrik Lorentz derived the same contraction independently and embedded it in a mathematical framework. Both men saved the ether for another decade, but at a cost. The contraction they proposed had no independent justification, no mechanism, no prediction that could be tested separately from the very phenomenon it was invented to explain. The fix worked only by construction. The null result had not destroyed the ether immediately, but it had made the ether unphysical in a way that one generation of physicists did not yet have the tools to articulate. Between 1861 and 1865, James Clerk Maxwell was not thinking about the speed of light. He was trying to solve a mathematical inconsistency in the equations governing electricity and magnetism, and the solution he arrived at was so unexpected that Maxwell himself spent years verifying its implications before committing to a public statement of what he had found. The inconsistency was small, almost pedantic in appearance. Ampere's law, which described how electrical currents produced magnetic fields, did not behave properly when applied to the charging plates of a capacitor. In the gap between the plates, where no current flowed, Ampere's equation produced a physically impossible result. Maxwell patched it by adding a new term, a displacement current arising from a changing electric field, which he invented entirely from mathematical necessity. No one had measured it. No one had suggested it. It existed only because without it, the equations did not balance. What Maxwell discovered when he combined his modified equations for empty space was that they predicted something that had never been observed and had no reason to be expected. When he eliminated the electric field from the pair of equations and solved for the magnetic field alone, and then repeated the process in reverse, he obtained a wave equation. The equations did not describe static fields or steady currents. They described a self-sustaining disturbance, an oscillating electric field generating an oscillating magnetic field, which in turn regenerated the electric field. The two locked together and propagating outward through empty space at a fixed speed. That speed was determined by two constants that had been measured in purely electrical and magnetic experiments: the permittivity of free space, which describes how electric fields behave in vacuum, and the permeability of free space, which describes how magnetic fields behave. Maxwell combined them and calculated a wave propagation speed of approximately 193,000 miles per second. He then looked at Fizeau's measured value for the speed of light, about 195,000 miles per second, and understood immediately what he had found. He wrote in his 1865 paper in the Philosophical Transactions of the Royal Society that the agreement between the two numbers was so close that it was scarcely possible to avoid the conclusion that light itself consisted of transverse undulations of the electromagnetic field. Electricity, magnetism, and light were a single phenomenon. The unification was complete, astonishing, and built entirely on a mathematical patch that Maxwell had added to fix an equation most physicists had not noticed was broken. Maxwell's equations were one of the greatest achievements in the history of science, and they contained a crisis that Maxwell did not resolve and that his contemporaries struggled to confront directly. The crisis was quiet, almost invisible when you first read the equations, but it was there in every line. Maxwell's equations predicted the speed of electromagnetic waves with precision. They gave a number. What they did not give was a reference frame. Every wave speed known to 19th century physics was defined relative to its medium. Sound traveled at roughly 767 miles per hour relative to air at sea level, which meant its speed changed depending on how fast the observer moved through the air. A musician walking toward the source of a sound heard it at a slightly higher frequency than one standing still, because the musician was moving through the same medium as the sound. The speed of the wave was fixed relative to the medium, not relative to the observer. This was how waves worked. This was what a wave meant. Light was a wave. If it was a wave, it propagated through a medium. If it propagated through a medium, its speed was defined relative to that medium. But Maxwell's equations said nothing about any medium. They produced a number, c, that appeared to be an absolute speed with no preferred frame attached to it. This was scientifically intolerable to most physicists of the 1870s and 1880s, and the resolution they reached for was the ether. The medium had to exist. Maxwell's equations were simply incomplete in failing to mention it, and Michelson's interferometer would eventually detect the drift and close the gap. Then the interferometer found nothing. The ether wind was undetectable. The equations still gave no reference frame. The contradiction sat in the middle of physics for 18 years, generating repair proposals and contorted explanations and, from most of the community, a studied reluctance to look at it directly. In 1905, a patent clerk in Bern named Albert Einstein picked it up and, instead of repairing it, dismantled the assumptions underneath it. On June 30th, 1905, the journal Annalen der Physik received a paper from a 26-year-old Albert Einstein with the title On the Electrodynamics of Moving Bodies. Einstein had no university position, no laboratory access, no research advisor, and had spent the previous 7 years thinking about what it would mean to chase a beam of light. His paper contained no experimental data, no literature review in the conventional sense, and no deference to the mathematical gymnastics that Lorentz and Fitzgerald had used to patch the ether theory. It contained 2 postulates stated simply at the beginning, and the rest of the paper was their logical consequences. The first postulate said that the laws of physics are identical in all reference frames moving at constant velocity relative to one another. No experiment, anywhere in the universe, on a ship or a planet or a comet, can distinguish uniform motion from rest. This was not a new idea. Galileo had recognized something like it for mechanical systems, and most physicists accepted it informally. The second postulate said that light propagates through empty space at a fixed speed, independent of the motion of the source. A flashlight on a moving train emits light at sea relative to everything, regardless of the train's velocity. This second postulate was the bomb. The 2 postulates seemed reasonable in isolation. Together, they destroyed simultaneity. Consider the consequence directly. If an observer on the ground and an observer on a moving train each measure the speed of the same light beam and both get c, they cannot be measuring the same elapsed time between the same pair of events. The only free variable is time itself. 2 events that appear simultaneous to the observer on the ground cannot appear simultaneous to the observer on the train, because simultaneous is a statement about the equal elapsed time between events and 2 clocks, and if the speed of light is constant for both observers, the clocks cannot agree. Simultaneity was not a universal fact about the universe. It was a local agreement between observers at rest relative to each other, valid only in their shared frame. Everywhere else, the timing of events was relative. Everything built on fixed, universal time had to be rebuilt from the beginning, and what replaced it was stranger than almost anyone had imagined. Picture a train moving through a station at high speed, and inside the center of one of the cars, a flash of light goes off. Two things happen at once, depending on where you are standing. A passenger sitting in the middle of the car sees the flash expand outward in all directions, and the light hits the front wall and the back wall at the same moment. The distances are equal. The speed of light is the same in both directions. For that passenger, both events, light hitting the front, light hitting the back, are simultaneous. That conclusion feels obvious. The kind of thing you would not bother writing down. Now place an observer on the platform, motionless, watching the train roll past. The same flash goes off at the center of the car, and this observer also agrees that light travels at c in all directions. But here is the thing. During the brief time it takes light to cross from the center of the car to the walls, the train has moved forward. The back wall has rushed toward the point where the flash originated. The front wall has retreated from it. So the light traveling toward the back wall has a shorter distance to cover than the light traveling toward the front wall. Because the speed of light is constant for this observer too, the light reaches the back wall first. Two observers, one event. One of them sees the flash reach both walls simultaneously. The other sees the flash reach the back wall earlier. Neither is mistaken. Neither instrument is broken. The speed of light is not in dispute. What is in dispute is simultaneity itself. The idea that two events either happen at the same time or they do not, as a fact that everyone should agree on. Einstein published this thought experiment in 1905 as a direct consequence of his two postulates, and its logic is airtight once you accept that the speed of light is truly constant for all observers. The platform observer has no choice but to conclude that the two wall strikes happened at different times. The train passenger has no choice but to conclude they happened together. Simultaneity is not a universal fact about the universe. It depends on the relative motion of the observer. This was not a philosophical curiosity. Every framework in classical physics that treated time as a universal river flowing at the same rate for everyone, every law of mechanics, every notion of force applied at a given instant, was built on the assumption that simultaneity was absolute. Einstein had pulled that assumption out from underneath the entire structure, and what collapsed was not a minor technical detail. It was the foundation. The consequences spread outward immediately. If two observers can disagree about whether events are simultaneous, and both are correct, then they must also disagree about elapsed time between events and about the distance between points in space. These are not independent quantities. They are entangled in a way that classical physics had never recognized, because the entanglement only becomes visible at speeds approaching c, speeds no human or instrument had ever reached before the 20th century. What actually happened to time and to distance once simultaneity fell apart was something the mathematics of Lorentz and Fitzgerald had partially anticipated. But anticipating the math is very different from understanding the physics. Einstein had the physics, and what it said about moving clocks and measuring rods was about to make the universe feel genuinely strange. A clock, placed on a fast-moving rocket, observed from the ground, runs slow. The hands advance, the pendulum swings, the atoms oscillate, but each cycle takes longer from the ground observer's perspective than from the astronaut's. When the rocket returns, the astronaut has aged less than everyone who stayed behind. The effect is called time dilation, and the word dilation understates what is happening. Time itself, the rate at which the universe processes events, is not the same for observers in relative motion. The amount of slowing follows the Lorentz factor, a number greater than 1 that grows with speed. At 10% of the speed of light, the Lorentz factor is about 1.005, meaning a moving clock loses roughly 0.5% of its time compared to a stationary one. At 90% of light speed, the factor rises to about 2.3. At 99%, it reaches 7. The closer to c, the more the factor swells, compressing the traveler's experience of duration relative to everyone watching from outside. Length contracts by the same factor. A ruler on that moving rocket, measured from the ground in the direction of travel, is shorter than when it is at rest. At 90% of c, the ruler is only about 43% of its rest length. The shortening is real. If you could photograph the rocket passing by, the photograph would show a compressed object, but the astronaut inside does not feel compressed, because from the astronaut's frame, the ruler is still at rest and still full length. The length contraction, like the time dilation, is not a distortion of the measurement. It is a feature of the geometry of spacetime. These effects seem like science fiction until you look for them in places where they have to appear. Particle accelerators cannot be designed without accounting for time dilation. The lifetimes of unstable particles stretch predictably as their speed increases, and the accelerator rings have to be built long enough to let those stretched lifetimes play out before decay. Precision atomic clocks flown in aircraft around the Earth come back with readings that differ from ground clocks by exactly the amount relativity predicts, a result confirmed multiple times to extraordinary precision. The Global Positioning System, a network of satellites that billions of people use daily without thinking about it, corrects for relativistic clock effects as a matter of routine engineering. The connection back to the speed of light is not accidental. Time dilation and length contraction are not separate phenomena bolted onto relativity as afterthoughts. They are the universe's way of preserving the one thing that cannot change, the speed of light. Every observer, regardless of motion, must measure c as the same value. For that to be true, their clocks and rulers must differ. The constancy of c and the relativity of time and space are not two ideas. They are one idea, seen from different angles. What Einstein had done was replace the question, how fast is light, with the deeper question of why that speed is the same for everyone. The answer pulled physics toward a complete reimagining of what space and time even are. But 12 years later, a young physicist would come at the same question from a completely different direction, using the machinery of quantum mechanics rather than geometry. And what he found inside that machinery would suggest that the speed limit was even more deeply embedded in reality than Einstein's picture had shown. The path he followed to get there was one that nobody had thought to walk before. And it started with a simple, outrageous idea about how particles move. Richard Feynman was 23 years old and working on his doctoral thesis at Princeton when he started wrestling with a problem that had bothered him since undergraduate physics. The existing formulations of quantum mechanics were powerful but ugly. They had been assembled in the 1920s through inspired guesswork and mathematical intuition, and they worked beautifully, but nobody could clearly explain what they meant physically. The wave function, the central object in Schrödinger's formulation, evolved through time according to a differential equation that told you probabilities, but it said nothing vivid about what a particle was actually doing between measurements. Feynman had been talking with his advisor, John Wheeler, about an old paper by the physicist Paul Dirac, who had noticed a curious connection between the quantum mechanical amplitude for a particle to travel between 2 points and the classical action, a quantity from Lagrangian mechanics that has to do with the difference between kinetic and potential energy integrated over a path. Dirac had noted the connection and moved on. Feynman looked at it and decided to take it seriously. His idea was this: instead of asking what path a particle takes from one point to another, ask about all possible paths simultaneously. Every conceivable trajectory between the starting point and the destination contributes to the final quantum amplitude. The straight line contributes. The parabola contributes. The path that goes to the other side of the galaxy and comes back contributes. The path that loops backward in time and then forward again contributes. Every path in the entire infinite collection of possible trajectories between 2 points carries a weight, and the total amplitude for the particle to arrive is the sum of all those weights added together. This was not a metaphor for ignorance about the real path. Feynman was proposing something stranger. The particle, in a precise mathematical sense, explores every trajectory before arriving at its destination. all paths are physically real, at least provisionally, and reality is what emerges from the sum. The proposition sounded like madness. If particles explored every path, including paths that looped around the galaxy, why did anything ever arrive anywhere in a reasonable amount of time? Why did quantum mechanics agree with classical mechanics at large scales, where particles obviously follow definite trajectories and do not explore the cosmos between measurements? Feynman had the answer ready. What happened when you actually added up all those contributions was more subtle and far more beautiful than anyone expected. But the full picture required understanding what each path contributed and how those contributions interacted. And that part of the story involved a kind of voting that the universe performs constantly, at every scale, without pause. Each path in Feynman's formulation carries a specific weight, expressed as a complex number with a magnitude and a direction. Physicists call this direction the phase, and it rotates continuously, like the hand of a clock, as you move from one path to a neighboring one. The rate at which the phase rotates depends on the action of the path, the quantity Dirac had noticed, which encodes how far the path deviates from the classical trajectory. Paths very close to the classical one have nearly the same action and therefore nearly the same phase. Paths far from the classical trajectory have wildly varying actions and phases that spin rapidly and unpredictably as you scan across them. Adding up complex numbers is equivalent to placing arrows end to end and seeing where the total points. When arrows all point in roughly the same direction, they reinforce each other and the total is large. When arrows point in random directions, they cancel. Short arrows pointing right, then up, then left, then down, then right again. The sum zigzags back towards zero. This is exactly what happens with the exotic paths in Feynman's sum. The path that routes a particle through the far side of the Andromeda galaxy has some specific action. The path right next to it, differing by an almost imperceptible detour, has a very different action, because small changes in wildly deviant paths produce large changes in action. The phases of neighboring exotic paths are completely uncorrelated. Add up their contributions, and they cancel almost perfectly. The more exotic the class of paths, the more thorough the cancellation. This is not a result that requires the universe to forbid strange paths. The universe does not put up a sign saying the long route is prohibited. The cancellation is democratic. Every path votes. The strange paths simply outvote each other into irrelevance, because no two neighboring strange paths agree on which direction to point. The cancellation is what makes classical physics appear as a limit of quantum mechanics. When you look at a baseball flying through the air, you are observing the macroscopic average of a process in which the ball's constituent particles are summing over all conceivable trajectories. The quantum fluctuations cancel into insignificance at that scale, leaving behind only the net contribution from the paths that survived the vote, and those paths are clustered tightly around the classical trajectory. The ball falls in a parabola because every other contribution has been voted out of existence by its own neighbors. What made Feynman's formulation so powerful was that it derived the classical world from quantum mechanics automatically, without having to assume that particles are different objects at large scales. The transition from quantum to classical was not a philosophical choice. It was a mathematical consequence of how waves and phases add. And if you followed this logic all the way to the behavior of light, you arrived at something even more striking. The reason light travels in straight lines had nothing to do with straight lines being special. Something else entirely had been deciding the outcome all along. Pull the lens in close to the classical path, the route that light appears to take between a source and a detector, and something qualitatively different emerges from the sum over all paths. The paths in this neighborhood have actions that differ only very slightly from the action of the classical trajectory. Because the action is nearly stationary here, varying slowly across neighboring paths, the phases of nearby paths all point in nearly the same direction. The arrows reinforce instead of cancelling. The sum accumulates. This is Fermat's principle of least time, derived from scratch. The 17th century mathematician Pierre de Fermat had observed that light always takes the path that requires the least travel time between 2 points, but he had no explanation for why the universe would honor such an elegant rule. Feynman's formulation answers the question completely. Light does not take the shortest path, because nature has a preference for brevity. Light appears to take the shortest path because the constructive interference of quantum amplitudes peaks there. At any point away from the classical trajectory, neighboring paths begin to disagree in phase, and their contributions start cancelling. The classical path is simply where the cancellation stops and the reinforcement begins. The same logic derives the law of reflection. Light bouncing off a mirror appears to take the path where the angle of incidence equals the angle of reflection. Every other angle is real in the quantum sum, but the contributions from non-classical reflection angles cancel among their neighbors, and only the classical angle survives. Snell's law of refraction, describing how light bends at the boundary between two materials, falls out the same way. Every optics law that was discovered empirically over centuries and encoded in geometric constructions turns out to be the shadow of a quantum mechanical interference pattern. The reason this matters for the speed of light goes deeper than optics. The sum over paths is only mathematically coherent if the phase associated with each path has a specific relationship to the action. Change the relationship and the cancellation pattern changes, the interference structure changes, and the apparent trajectory changes. The classical path that survives the vote is the one consistent with the fundamental equations of the theory, and those equations, at the relativistic level, are constructed around the invariant speed c. In other words, the reason light appears to move in a straight line at a fixed speed is embedded in the same quantum mechanical architecture that governs every particle in the universe. The speed limit is not imposed from outside the quantum theory. It is internal to the structure of how amplitudes add and cancel. Feynman had arrived at the speed of light not through geometry, as Einstein had, and not through electromagnetism, as Maxwell had, but through the deepest formulation of probability in physics. And buried in the equations that made all of this work was a constraint on massless particles that went well beyond anything that classical physics had ever needed to state. The relativistic energy-momentum relation, one of the central results of special relativity, connects a particle's energy, its momentum, and its rest mass through an equation involving c. Written out carefully, it says that the square of a particle's total energy equals the square of its momentum multiplied by c squared, plus the square of its mass multiplied by c to the fourth power. For a particle with mass, this produces a family of possible energies and momenta, all consistent with the particle moving at speeds below c. Set the mass to 0, and the equation simplifies to something with no free parameters. Energy equals momentum times c, full stop. There is no adjustable quantity left. The relationship between energy and momentum is locked to a single fixed ratio. When you ask what velocity this corresponds to, the answer is the one speed at which energy and momentum stand in exactly that ratio, c and only c. A massless particle moving at any speed other than c would have energy and momentum in a ratio incompatible with the equation, which means it could not exist in a consistent way. It would carry energy and momentum values that satisfy no valid relativistic trajectory. The mathematics does not produce a slower version of such a particle. It produces nothing. A massless particle moving slower than c is not an exotic object. It is not even a theoretical curiosity. It is simply non-existent, ruled out not by a physical force or barrier, but by the internal consistency requirements of the equations. This is a different kind of prohibition from anything in classical physics. Classical physics could imagine a particle that moved at any speed. The speed was just a number you plugged in. Relativistic quantum mechanics closes that door. For massless entities, speed is not a variable. Speed is the only possibility consistent with their mass, which is to say, consistent with being real. Photons, the quanta of light, are massless. Their speed at c is therefore not a coincidence of their nature as light carriers. It is a mathematical requirement of their having no mass. If you built a universe where light was carried by particles with a tiny but non-zero mass, those particles could in principle travel at a range of speeds, and the behavior of electromagnetic waves would be radically different. The universe we inhabit has photons that are massless to an extraordinary precision, tested to better than 1 part in 10 to the 54th power in some experiments, and so they travel at c without exception. But the wall that massless particles hit is qualitatively different from the wall that massive particles approach. Massive particles do not hit a wall. They approach one that grows taller the closer they get. A wall made not of any material but of energy requirements that compound on themselves without limit. Understanding that compounding was what made the full strangeness of the speed barrier visible, and the numbers involved were unlike anything in ordinary experience. Take a proton at rest, give it energy, it starts to move. Double the energy and it moves faster. For a while, the relationship feels almost normal. More energy means more speed. But as the speed climbs towards c, something changes. The energy you pour in stops becoming speed and starts becoming something else entirely, a quantity that physicists call relativistic mass, the effective inertia of a moving object which grows without bound as velocity approaches c. The Lorentz factor governs this growth. At 90% of light speed, the factor is approximately 2.3, meaning the proton resists further acceleration as if it were 2.3 times heavier than when it was at rest. At 99% of c, the factor is about 7. Accelerating the proton further requires 7 times as much force for the same result as it took near rest. At 99.9%, the factor reaches about 22. At 99.99%, it is over 220. The pattern does not plateau. Each additional 9 added to the decimal makes the factor larger by a ratio of roughly 3.5. The energy required to push a proton from 99.9% of c to 99.99% is approximately the same as the energy required to accelerate it from rest to 99% in the proxus, first place. The wall does not get gradually steeper. It gets steeper faster than it gets steeper, each increment costing more than the sum of all previous increments combined. Reaching c for a massive particle would require the Lorentz factor to be infinite, which means infinite energy. There is no large enough number. There is no energy source adequate. The limit is not an engineering constraint waiting to be solved by better technology, as humans have solved so many other constraints by building cleverer machines. The limit is a mathematical statement that an infinite quantity cannot be supplied. What makes this concrete is that particle accelerators have been probing this wall for decades, pouring colossal amounts of energy into individual particles and watching the speedometer inch upward with diminishing returns. The numbers from those accelerators are precise, and they tell a story about the wall that is perfectly consistent every single time with what Einstein's equations predict. Something in nature respects that boundary absolutely, and the machines at the European Organization for Nuclear Research have been testing it at the highest energies ever achieved. What they found there confirmed the wall more completely than any previous experiment in history. Every second, somewhere above Earth's atmosphere, high-energy particles from deep space collide with nitrogen and oxygen atoms, about 9 miles up, and shatter them into showers of secondary particles. Among the debris are muons, heavy relatives of the electron with a rest mass about 200 times larger. The muon is unstable. Left alone, it decays into an electron and 2 neutrinos in an average of 2.2 millionths of a second. That lifetime has been measured in laboratories with high precision. It is not approximate. It is a property of the particle as fundamental as its charge. Do the arithmetic. A muon moving at nearly the speed of light, say 99% of c, covers about 2,000 feet in 2.2 microseconds before decaying. The atmosphere is about 30,000 feet thick at sea level. A muon produced 9 miles up under the most optimistic assumptions about its speed, should decay somewhere over the ocean, far above the detectors sitting on the ground. Muon detectors at sea level should register very few, or perhaps none. They register thousands per square yard per hour. The muons arrive because their internal clocks run slow. Moving at 99.94% of c, their Lorentz factor is approximately 29. From the muon's frame of reference, its lifetime is still 2.2 microseconds, because its clock runs at its own rate. But from Earth's frame, that internal clock runs 29 times slower. 2.2 microseconds of muon time becomes 64 microseconds of Earth time, long enough to travel the full 9 miles and reach the ground. Time dilation is not a theoretical curiosity confined to thought experiments and global positioning system satellites. It arrives on the surface every second in the form of particles that should not be there. Physicists have confirmed this in particle storage rings, where muons circulate at controlled speeds and their decay rates are measured precisely. At 99.94% of c, their effective lifetime stretches by a factor of 29, matching the prediction to better than 1 part in 1,000. Every version of this experiment, at every speed, tested across multiple laboratories and decades, has produced the same result. Time dilation works exactly as relativity predicts, consistently, without deviation, all the way up to the speeds accessible to particle physics. The muon experiment became one of the clearest demonstrations that special relativity describes something real rather than something mathematical. 2.2 microseconds is not a number that can simply be stretched by willpower or engineering. It is a property of the particle, and the only thing that stretches it is the geometry of space-time itself. Something in the structure of the universe, the same structure that enforces the speed of light, had reached down and extended the muon's life to allow it to exist where it had no business being. That same structure was also, at that very moment, silently running inside every mobile telephone on Earth. Every phone that uses satellite positioning is running a correction that Einstein would have recognized immediately. The satellites in those networks orbit approximately 12,500 miles above Earth's surface, moving at roughly 8,600 miles per hour relative to the ground. That velocity is nowhere near the speed of light, but it is fast enough for the effects of special relativity to accumulate into something consequential. Because the satellites are moving relative to ground receivers, their onboard clocks tick slightly slower than identical clocks sitting on the surface. The Lorentz factor at 8,600 miles per hour is tiny, but it applies continuously, and over 24 hours, the satellite clocks fall behind ground clocks by about 7 microseconds. 7 microseconds sounds trivial. Light travels about 2 miles in 7 microseconds, but positioning systems determine location by timing how long signals take to travel from satellite to receiver. An error of 7 microseconds in the timing corresponds to an error of about 2 miles in the computed position. Accumulated over a day without correction, this would make the system useless for any application requiring accuracy better than miles. The correction for this effect is built into the satellite firmware before launch. But special relativity is only half the story. General relativity, Einstein's later and more comprehensive theory of gravity, predicts that clocks in weaker gravitational fields run faster than clocks in stronger ones. Satellites are farther from Earth's center than ground receivers and therefore experience weaker gravity. Their clocks run faster for this reason by about 45 microseconds per day, more than 6 times the special relativistic effect, and in the opposite direction. Combined, the two effects produce a net gain of 38 microseconds per day for the satellite clocks relative to the ground. Engineers designing the first satellite positioning systems in the 1970s debated whether relativistic corrections were necessary. Some argued that the effects were too small to matter in practice. The physicists disagreed, and the physicists were right. Without the corrections, position errors would compound at roughly 7 miles per day, rendering the system worthless for navigation within hours of operation. Every satellite in the network carries firmware that applies both relativistic corrections continuously. Special relativity enforces the speed of light as an absolute boundary in the abstract geometry of spacetime. General relativity connects that geometry to gravity and acceleration. Both theories leave fingerprints on a device that most people regard as a consumer product rather than a relativistic instrument. The agreement between the predictions and the engineering requirements is exact, not approximate. Relativity does not fail at the level where technology depends on it. This is what physics looks like when the theory is correct, and the machines at the very edge of human engineering had just begun to show how correct it was. Inside the tunnel that forms a ring 17 miles in circumference, beneath the farmland outside Geneva, Switzerland, protons travel in both directions simultaneously, guided by superconducting magnets cooled to temperatures colder than deep space. The European Organization for Nuclear Research operates this machine, the Large Hadron Collider, and among its purposes is the acceleration of protons to energies not seen in nature since the first moments after the origin of the universe. The machine pushes protons to energies of 6,500 times their own rest mass. The velocity that corresponds to is not 99% of c, or 99.9%, or a version with a handful of nines. The actual figure is 99.9999991% of the speed of light. Writing it out requires 8 nines after the decimal, followed by a 1. At that speed, the Lorentz factor is approximately 6,900. The proton's effective inertial resistance is nearly 7,000 times its rest mass. Pump in more energy, and the speed creeps upward by a fraction, so small it is genuinely difficult to express, from 99.9999991% to 99.999999992%. A change in speed smaller than 1 part in 10 million of an already overwhelming fraction of c. Engineers at the facility measure everything. The energy input is tracked. The velocity is inferred from the behavior of the particles in the magnetic fields. The collision products are analyzed by detectors the size of apartment buildings. Across every run, at every energy level, across every year of operation, no proton has reached c. Every energy increment produces a smaller and smaller velocity increment. The relationship between energy added and speed gained follows the Lorentz factor with extraordinary precision, deviating from Einstein's prediction by an amount too small to measure. The machine is not trying to break the speed limit. The engineers and physicists know that is impossible. They are using the machine to study what happens when protons collide at these energies, a different set of questions entirely. But the wall is always there, visible in the data, as reliable as any physical constant ever measured. 6,500 times rest mass energy, and the speed has moved to within less than 1 part in a billion of c, and gone no further. The barrier is not technological. The barrier is mathematical, as exact in a 17-mile ring of superconducting magnets as it is in the equations Feynman wrote by hand in a Princeton graduate office. And what those equations said about the geometry underlying all of it, the deeper reason the wall existed at all, had been waiting to be fully articulated for 40 years. The facility in Livingston, Louisiana, barely looks like the most sensitive measuring instrument ever built. From the outside, it resembles a long, low building set at the junction of 2 concrete tubes stretching off into pine forest, each about 2.5 miles long. Inside those tubes, laser beams bounce between mirrors, polished to within a fraction of an atomic diameter, measuring the distance between those mirrors to a precision smaller than 1,000th the width of a proton. Engineers built it to detect something that most physicists, even at its conception, privately doubted would ever be found within a human lifetime. On September 14, 2015, at 5 minutes to 10 in the morning, Greenwich time, it found one. The signal lasted approximately 0.2 of a second. It began as a gentle oscillation, then rose in frequency and amplitude like a chirp. then stopped. Both the Louisiana detector and an identical facility in Hanford, Washington registered it. Louisiana first, Washington 7 milliseconds later, a gap precisely consistent with a wavefront traveling at the speed of light across the approximately 1,800 miles separating the two sites. Researchers spent months examining the data before publishing. The instrument had recorded a distortion in space itself, a stretching and squeezing of the physical distance between mirrors caused by a gravitational wave passing through the Earth. The source, calculated from the signal's shape and strength, was two black holes merging roughly 1.3 billion light-years away, an event that had happened when complex life was only beginning to appear on Earth, sending ripples outward at the speed of light that arrived here on that September morning. Gravitational waves, predicted by Einstein's general relativity in 1916, carry energy and propagate through spacetime. The question of whether they travel at exactly the speed of light, or at some slightly different speed, determined by an as-yet unknown theory of quantum gravity, had stayed open for decades. A dramatic answer arrived 2 years later. On August 17, 2017, a gravitational wave detector picked up the signal from two neutron stars spiraling inward and colliding approximately 130 million light-years away. 70 observatories on the ground and in space trained themselves on the same patch of sky. A gamma-ray burst, the most energetic electromagnetic event in the known universe, arrived at the Fermi Gamma-Ray Space Telescope 1.7 seconds after the gravitational wave signal. After a journey of 130 million light-years, the two signals arrived separated by less than 2 seconds. That tiny gap represents the difference in travel time of gravity and light, constraining their speeds to agree within 1 part in 10,000 trillion. Gravity and light travel at the same speed. They travel at c. The significance runs deeper than confirming a number. Electromagnetic radiation obeys Maxwell's equations, whose constants force light to travel at c. Gravitational waves are entirely different entities generated by a completely different field equation, describing the curvature of spacetime rather than electromagnetic oscillations. For both to arrive at the same cosmic speed limit, for two entirely different sectors of physics to independently converge on c, means the limit is more fundamental than any single force or particle. It is a property of the geometry that every physical process, regardless of its nature, must respect. That unity should settle the question forever. And yet, just 6 years before that neutron star measurement, a single loose cable had almost convinced the world otherwise. The detector sat under a mountain in central Italy, in a laboratory cut from the rock of the Gran Sasso Massif at nearly half a mile of depth. The experiment, called Opera, was designed to study neutrinos, nearly massless particles that interact so weakly with ordinary matter they stream through the entire Earth without noticing. The detector was built to catch the tiny fraction that happened to interact with its target mass, accumulating data from a beam of neutrinos fired in pulses from the European Organization for Nuclear Research near Geneva, approximately 454 miles away. The experiment was not designed to test the speed of light. What happened in the autumn of 2011 turned it into the most talked about physics result in a generation. Researchers noticed that the neutrinos were arriving too early. Not by much, just 60 nanoseconds per trip, roughly 60 billionths of a second. Over the 450 miles of rock and crust the particles traversed, 60 nanoseconds corresponded to a speed fractionally above c, approximately 1 part in 40,000. The team spent 6 months checking every conceivable source of error, testing and retesting the timing systems, the distance measurements, the satellite corrections, and the statistical analysis. They submitted the result for peer review in September 2011 with a confidence level of 6 standard deviations, the threshold the field requires to declare a discovery. The announcement caused an immediate sensation that is difficult to overstate. Hundreds of theoretical papers appeared within weeks. Physicists who had spent careers working within the constraints of special relativity began preparing frameworks that might accommodate a world where the limit was not absolute. News coverage around the world declared that Einstein might finally have been proven wrong. The result was significant enough that researchers at the independent Icarus experiment, also housed at Gran Sasso, were already designing a cross-check when the Opera team made a second announcement in February 2012. They had found two problems. The first was a loose connection in a fiber optic cable linking a global positioning system receiver to the master clock used to synchronize the timing. When investigators pushed the cable firmly into its socket and repeated the measurement, the anomalous arrival time shrank by approximately 73 nanoseconds, almost exactly the size of the claimed effect. The second problem was an oscillator in the same timing circuit that had been running slightly fast, pulling the measured arrival time in the opposite direction. Corrected for both errors, the neutrinos arrived precisely when special relativity predicted they should. Icarus published its own measurement shortly after, finding neutrino speeds consistent with c within their experimental uncertainty. Subsequent experiments at other facilities confirmed the same conclusion. The most excited physics result in a generation had been produced by a cable that was not fully pushed in. What the episode revealed was not a failure of science, but a demonstration of how it works. The Opera team had been correct to publish after their own extensive checks. Extraordinary claims demand scrutiny from outside the original group, and that scrutiny arrived rapidly. The error was found, corrected, and the result was overturned within 5 months. The speed limit held, not by consensus or authority, but because the universe itself enforced it when the measurement was done properly. The limit keeps holding, but understanding why requires knowing what, exactly, is not violating it. Because the universe contains several things that look, at first inspection, like they might. Quantum entanglement feels like it should break the rule. Two particles are prepared in a shared quantum state, then separated by any distance, even across a continent or between two satellites. When a measurement is made on the first particle, the second particle's state becomes definite instantaneously, with no delay proportional to the distance between them. The correlation is real, confirmed by hundreds of experiments, and its speed cannot be assigned any finite value. A version of this experiment performed in the Canary Islands in 2017 separated the two particles by more than 700 miles, and the correlation appeared without measurable delay. Here is why this changes nothing. The correlation only becomes useful, only becomes visible as information, when the results of both measurements are compared. That comparison requires a conventional signal, a phone call, a radio transmission, something physical traveling at or below c. Without that comparison, the observer who measured the first particle sees only a random outcome, and the observer who measured the second sees only a random outcome. Neither knows whether their result is correlated until they exchange information by ordinary means. The non-local correlation is real, but it cannot carry a message. Distant galaxies present a different kind of apparent violation. Galaxies far enough away are receding from us faster than c, confirmed by precise measurements of light stretching over cosmological distances. Those galaxies are not moving through space at that speed. Space itself is expanding, carrying them along. The expansion of space is governed by general relativity, not special relativity, and general relativity places no limit on the rate at which space can expand. The distinction between objects moving through space and space itself expanding is not a technicality. No galaxy in the visible universe locally exceeds c, relative to its immediate surroundings. Shadows can also appear to exceed c with modest effort. Rotate a laser pointed at a distant surface fast enough, and the dot sweeps across that surface at a speed limited only by the rotation rate and the distance. At a large enough distance, the dot's motion exceeds the speed of light easily. Ripples of light, spreading along a curved surface, effects called light echoes, can sweep across a nebula faster than c for the same geometric reason. In each case, the same analysis applies. The dot sweeping across the wall is not a physical object. No mass moves along that path. No energy is transmitted from one end of the sweep to the other. No signal travels between points on the wall at the dot's apparent speed. The shadow carries no information. The light echo carries no information from one place along its path to another. Every apparent violation, examined carefully, turns out to be an illusion of geometry or a confusion between motion and information transfer. The limit stands, uniform and consistent. But behind every one of these illusions lurks a deeper question. What would it actually mean if something could carry information faster than c? The answer involves causality, and the answer is catastrophic. Cause precedes effect. That statement seems so basic, it barely qualifies as a physical law, closer to a definition of what cause means. Every event in experience confirms it. The spark precedes the flame. The push precedes the motion. The transmission precedes the receipt. The asymmetry between cause and effect is so woven into how reality works that imagining it otherwise requires genuine effort. Special relativity does not threaten this ordering for anything traveling below the speed of light. The moment a signal crosses that threshold, the ordering does not just bend, it breaks. The mathematics is straightforward, derived directly from the Lorentz transformation, the same equations that give time dilation and length contraction. Consider two events, a transmission at point A and a reception at point B, separated in space. For any signal that connects them traveling at or below c, every possible observer, regardless of their velocity, agrees that the transmission happened before the reception. The time ordering is preserved for all inertial frames, no exceptions. Allow the signal to travel faster than light. Choose an observer moving at a perfectly ordinary subluminal speed in the right direction, and the Lorentz transformation produces a startling result. For that observer, the reception at point B occurs before the transmission at point A. The observer sees the reply before the message. The effect precedes the cause. This is the direct mathematical output of the transformation rules, derived from Einstein's two postulates, and it is unambiguous. The problem scales. One observer experiencing reversed causality might seem like a tolerable oddity, but observers can communicate with each other. The observer who sees the reception before the transmission can transmit their own message, and from a third reference frame, that message might arrive before it was sent. Chain these reversed causality connections together, and the structure of the universe becomes inconsistent. Consider what this means practically. A faster-than-light signal sent from Earth to a distant station could, from the correct reference frame, be received before it was sent. If the station immediately responds with another faster-than-light signal, that response can arrive at Earth before the original transmission departed. The sender, looking at the reply already in hand, has a choice about whether to send the message. Depending on what the reply contains, they might decide not to. But if the message was never sent, the reply never existed. If the reply never existed, there was nothing to prevent sending it. So the message was sent, so the reply was generated. So the decision was made not to send. The causal chain has no self-consistent resolution. The speed of light is not a speed limit the universe imposes reluctantly, the way a camera enforces a highway restriction. It is the exact boundary at which the causal structure of spacetime remains intact. Cross it, and the consistency dissolves. There is even a specific name for the worst version of this scenario. It was worked out carefully more than a century ago, and it is more disturbing than the simple reversed order case. Richard Chas Tolman was a theoretical physicist at the California Institute of Technology who, in 1917, formalized a problem Einstein had sketched out in a private letter a decade earlier. The setup is spare and precise, and its conclusion is unavoidable. Later, physicists named it the tachyonic antitelephone, a reference to the hypothetical faster-than-light particle called a tachyon. Observer A and Observer B are in relative motion. Observer A sends a faster-than-light message to Observer B. Because they are in relative motion and the signal travels faster than light, the Lorentz transformation places the reception at a specific point in spacetime. Observer B, upon receiving the message, immediately sends a faster-than-light reply back to observer A, because observer B is also in motion relative to A, and because the reply also travels faster than light. The Lorentz transformation places the arrival of the reply at a point in spacetime that is, for observer A, before the moment observer A sent the original message. Observer A receives the reply before sending the message. At that moment, observer A has a choice. The reply is already in hand. Observer A can decide, based on whatever the reply contains, not to send the original message. If the message is never sent, observer B never receives it. If observer B never receives it, the reply was never generated. If the reply was never generated, observer A never received it. If observer A never received it, nothing prevented sending the original message. So the message was sent, so the reply was generated. So observer A received it, so the message was not sent. There is no self-consistent solution to this loop. Every possible version of events either requires the message to be sent or requires it not to be sent, and both options lead back to the opposite requirement. The system has no stable state. It cannot happen. Physicists say faster-than-light communication would violate causality, and that is accurate but understates the severity. Breaking a causal loop does not produce an unexpected measurement. It produces a universe that cannot self-consistently exist. The chain of reasoning arrives not at a wrong prediction but at a logical impossibility, the kind that does not resolve itself when you gather more data. Tolman's construction follows directly from Einstein's postulates. The anti-telephone is not a puzzle imported from outside physics. It is a derivation from inside it, using only the mathematics of special relativity and the assumption of a faster-than-light signal. What makes this remarkable is that the problem is not about the speed of the signal specifically. Any speed above c, no matter how slightly, allows the construction to work. The boundary at c is exact, and the question of why that exact boundary also happens to match the speed of light, why the geometry of spacetime has precisely this property and not some nearby variant, opens a door into territory that even physicists, who have spent decades on these questions, find genuinely unsettling. The tachyonic antitelephone is a clean version of a broader category of problems that share a single structure, a chain of causes that loops back on itself, each event requiring the previous event that it also prevents. Physicists call these closed causal loops, and the thought experiment that most people encounter first is the grandfather paradox. Suppose a person builds a time machine and travels back to a period before their parents were born. They find their grandfather as a young man and prevent him from ever having children. Their parent is never born. They are never born. They never build the time machine. They never travel back. Their grandfather lives a full life, has children. The parent is born. The person is born. The machine is built. The trip is made. The loop has no stable resolution. Unlike the tachyonic antitelephone, this paradox involves time travel directly rather than faster-than-light communication, but the underlying structure is identical. Both require a signal or influence propagating along a path that, in space-time geometry, arrives before it departed, forming a closed loop in the causal order. The relationship between faster-than-light travel and time travel is not incidental. In the Minkowski geometry of special relativity, a path connecting two events that no light signal could connect in the available time is equivalent to a path that runs backward in time from certain reference frames. The two concepts are the same geometric object viewed from different angles. Some physicists have argued that closed causal loops might be allowed by the universe, provided they are self-consistent, meaning history always arranges itself so that no contradiction arises. The physicist Igor Novikov formalized this as the Novikov self-consistency principle. Any event in a causal loop must be consistent with all other events in the loop, and the universe permits only those outcomes that do not produce contradictions. In this view, you could travel back in time, but you could never actually prevent your grandfather from having children. Every attempt would fail, not because of some external force, but because consistency demands it. The self-consistency proposal sounds tidy until you push it. It requires that for every possible action a time traveler might take, the universe arranges a result that is both locally plausible and globally consistent with the entire loop. For complex loops with many decision points, this demands that an enormous number of independent events each come out just right. Some physicists find this demand so implausible that they argue it effectively prevents the loop from forming at all. Others accept it as a logical possibility that simply restricts what can happen in the loop, not whether the loop can exist. Both camps share the conclusion that faster-than-light travel cannot be made consistent without imposing restrictions so severe that the original purpose is defeated. Either the loops cannot form, or they can form only in versions that prevent the very actions they seem to allow. The speed limit and the causal order are not two separate constraints. They are the same constraint expressed in different terms. The universe, it seems, has a mechanism for enforcing this. One physicist described it not as a law but as a tendency, something embedded so deeply into the structure of space-time that it operates automatically before the paradox can fully crystallize. In 1992, Stephen Hawking published a paper in the journal Physical Review D with a precise and confident title, Chronology Protection Conjecture. The paper proposed that the laws of physics conspire, through mechanisms already present in general relativity and quantum field theory, to prevent the formation of what physicists call closed time-like curves. A closed time-like curve is the technical name for a path through space-time that loops back on itself in the time direction. The formal definition of a time machine, Hawking's argument rested on a feature of quantum field theory in curved space-time. When a space-time region approaches the conditions necessary for a closed time-like curve to form, the quantum vacuum responds with divergent behavior. Virtual particles and field fluctuations that exist in normal space-time circulate around and around the loop as the loop nearly closes, accumulating energy with each pass. Before the loop can fully form, the energy density of the quantum vacuum in that region grows without bound, generating a stress energy that curves space-time back away from the time loop configuration. The universe absorbs the causal paradox before it can crystallize into reality. Hawking was careful to call this a conjecture rather than a theorem because nobody had derived it rigorously from first principles. The calculations involved quantum field theory in curved space-time, a domain where the mathematics becomes extraordinarily difficult and where the full theory of quantum gravity, which does not yet exist, would be needed to make definitive statements. Hawking was describing a tendency observed in the limited cases that could be analyzed, not a proven law. He supported the conjecture with what he called empirical evidence, the fact that we have not been invaded by tourists from the future. If time travel to the past were possible, even in principle, some future civilization at some point in the history of the universe would have built a machine capable of it. The machine would presumably have been used to send visitors to every moment in the past, including our present. Observing no such visitors is at least consistent with the conjecture, and it is a form of evidence, even if indirect. The conjecture has neither been proven nor definitively refuted in the decades since its publication. Certain specific space-time configurations have been analyzed and found to be protected in the sense Hawking described. Others remain ambiguous. What the conjecture has done is focus attention on a specific mechanism by which the speed limit and causal ordering enforce themselves, not as external rules imposed on the universe from outside, but as a consequence of the universe's own self-regulation through quantum effects. The deeper point is this: the speed of light and causality are not two separate physical laws that happen to be numerically related. They are two descriptions of the same geometric fact about space-time, and that geometry was written down most clearly by a mathematician who had once failed to recognize the revolutionary potential of his most famous student. Hermann Minkowski was Einstein's mathematics professor at the Zurich Polytechnic, and he had not been impressed. He described his student as a lazy dog who rarely attended lectures. When Einstein published Special Relativity in 1905, Minkowski initially set it aside. By 1908, he had understood what Einstein had done, reframed it in the language of geometry, and produced a formulation so clear and powerful that Einstein himself eventually said Minkowski had made relativity truly comprehensible. Minkowski's key move was to treat time as a fourth dimension alongside the three spatial dimensions, but with a crucial difference in how distance was measured. In ordinary three-dimensional space, the distance between 2 points is the square root of the sum of the squares of the differences in each coordinate: east-west, north-south, up-down. This formula produces a number that every observer agrees on regardless of their orientation. Rotate the coordinate axes and the individual components change, but the total distance remains fixed. It is an invariant. Minkowski defined an analogous quantity for spacetime, the spacetime interval, with one critical modification. The three spatial squares are added together in the usual way. The time coordinate multiplied by c is squared and then subtracted from the spatial total. That single minus sign is the entire difference between Minkowski's spacetime and ordinary four-dimensional space, and it changes everything. Because of that minus sign, the spacetime interval between two events can be positive, negative, or exactly zero. When positive, the events are separated in space by more than light could cross in the time between them. No causal signal can connect them. Their time ordering is reference frame dependent. When negative, the events are separated in time by more than a light signal would need to cross the spatial gap. A causal signal can connect them, and every observer agrees on their ordering. When the interval is exactly zero, the two events lie on the path of a light signal. A photon departing one event arrives precisely at the other. This surface, spreading out in all directions from a given event, is the light cone, the boundary between what can causally influence that event and what cannot. Everything inside the light cone can send or receive causal signals. Everything outside cannot. The light cone is the geometric shadow of that minus sign, present at every point in space-time, defining what is past, what is future, and what is forever unreachable. The structure encoded by that minus sign is called the Lorentzian signature of space-time. Mathematicians can write down space-times with two time dimensions or with all four dimensions carrying the same sign. These structures are mathematically valid. A universe built on them would have no light cones, no consistent causal ordering, no architecture that allows complex processes to build on previous complex processes. They would be universes without history. The minus sign is not a law about particles, it is a law about structure. And the deepest question in all of this is whether the structure is truly fundamental or whether it is a consequence of something deeper still. The name is misleading. It has been misleading since Römer first inferred it from the timing of Io's eclipses, and the misleading nature has grown more serious as physics has deepened. Physicists call c the speed of light, which implies it is a property of light, a characteristic that photons carry the way mass carries weight. The actual situation is the reverse. Light travels at c because of what c is, not the other way around, and what c actually is has almost nothing to do with light specifically. Consider what c does inside the equations of physics. In Maxwell's equations, c appears as the ratio of two electromagnetic constants, one governing electric fields and one governing magnetic fields, and the wave speed emerges from that ratio. In special relativity, c appears in the Lorentz factor as the speed that cannot be reached by anything with mass, and in the energy-momentum relation as the conversion between mass and energy. In Minkowski's spacetime geometry, c is the conversion factor between the time dimension and the spatial dimensions, the coefficient that translates seconds into meters so that both can enter the same equation on equal footing. In general relativity, c appears as a fundamental constant in Einstein's field equations, relating the curvature of spacetime to the distribution of energy and momentum. In each of these contexts, c is performing the same job, converting between units, specifically between units of space and units of time. The fact that these are different kinds of measurement, that we measure distance in miles and time in seconds, reflects a historical accident of human perception and culture, not a physical distinction. Space and time are components of a single geometric structure, and c is the constant that relates one to the other, the way a conversion factor relates inches to feet. Physicists who work with natural units, a common practice in quantum field theory and general relativity, simply set c equal to 1. When they do this, c disappears from the equations entirely. What remains are the physical relationships. Stripped of unit conversion clutter, the equations become cleaner and the structure becomes more visible. Mass and energy are the same thing, measured in the same units. Space and time are the same thing, measured in the same units. The speed limit is not a rule saying particles cannot go faster than a certain velocity. It is a statement that space and time are aspects of the same dimension, and the number we call c is the slope of that equivalence. Photons travel at c because they have zero mass. The energy-momentum relation for a massless particle reduces to a single requirement. Energy equals momentum times c, which is only satisfied at exactly c. A massless particle at any other speed would carry zero energy and zero momentum, and would be, in every measurable sense, non-existent. Photons do not travel at the speed limit because they are special. They travel at it because there is no alternative for something without mass. If no photons existed anywhere in the universe, the space-time geometry would still have the same Lorentzian signature. The light cones would still be there. Causal structure would still be defined. The conversion factor between space and time would still exist, waiting to be measured by whatever physical process happened to travel at the maximum speed. We named c after light because light was the first thing we found that traveled at the limit. The limit was always older. Richard Feynman was one of the most fearless questioners in the history of physics. He dismantled pretension, ignored authority, and followed logical chains wherever they led. When a student asked him why magnets repelled each other, he spent several minutes explaining why the question itself was harder than it sounded, then admitted that at the deepest level, the answer was that the universe was built that way, and that the building required no further justification the universe was willing to offer. Feynman applied the same honesty to the question at the center of everything discussed here. Why does space-time have the signature it has? 3 spatial dimensions with a positive sign and 1 time dimension with a negative sign. Why that structure and not some other? Nobody knows. Feynman did not know. No physicist working today knows. The answer is not hiding behind an equation that has not yet been written. The question has been posed precisely in rigorous mathematical language, and the response from the universe is silence. The Lorentzian signature of space-time is assumed in general relativity, assumed in quantum field theory, confirmed to extraordinary precision by every experiment ever run, and utterly unexplained as to why it should be this way and not another. The stakes of this question are concrete. Change the signature of space-time and you change everything that can exist. Give time a positive sign like the spatial dimensions, and the light cone disappears. Causal order dissolves. Events separated in time can be connected from any direction, and the consistent threading of cause through effect that allows complex structures to build and persist over time simply stops working. Atoms could not maintain stable orbits. Chemistry could not happen. Biology could not happen. No structure more complex than a momentary fluctuation could persist long enough to become anything. The value of c in miles per second is an accident of human history. We chose miles, we chose seconds, and those choices determine the numerical value of c. The way choosing miles per hour rather than feet per second changes the number describing a car's speed. The number itself carries no fundamental significance. The fine structure constant is different. Built from C, from the charge of the electron, from Planck's constant, from the permittivity of free space. When those quantities are combined, all the units cancel perfectly, leaving a pure, dimensionless number that comes out to approximately 1 divided by 137. It governs how strongly electrons interact with photons. It determines the structure of atoms, the behavior of chemistry, the opacity of stars, the color of everything. It is a number the universe chose, and no one knows why it chose that one. Feynman called it one of the greatest unsolved mysteries in physics and wondered for years whether some deep reason made it impossible for it to be otherwise. He died without finding the answer. What Feynman did uncover, in the path integral formulation, was something that reframes all of this. He showed that particles do not travel from one place to another because nature forces them along a specific path. Nature gives every possible path an equal vote: the straight line, the curved route, the trajectory that circles the galaxy. Every conceivable path is explored simultaneously, each carrying a rotating mathematical arrow, each contributing to the final result. The paths far from the classical trajectory cancel, their arrows spinning in opposing directions, their contributions annihilating each other. The paths near the classical trajectory reinforce, their arrows aligned, their contributions adding together. The laws of physics are not rules that forbid certain things. They are the consequence of everything being permitted and structure emerging from the cancellation. The speed of light, approached from this angle, is not a wall. A wall is something that stops you from going where you want to go. The speed of light is the geometry of the arena where everything happens. It is the shape of space-time that makes before and after meaningful, that allows a cause to produce an effect, that permits structure to persist long enough to become complex, that gives the universe a history rather than a noise. Every path is explored, every alternative is tried. What remains, when the impossible cancels, is a universe with edges, with time, with light, and with minds that can wonder why the edges are where they are. Feynman could not answer that last question. In the right kind of silence, that is the most honest thing he ever said.